Hi everyone, so as promised, this is the last video for chapter 2. We went over this briefly in class, but I wanted to specifically show you how to name compounds. Now, we are going to separate them into two types, ionic compounds and molecular compounds. As we know, ionic compounds are composed of metals and nonmetals. The way you name them is you take the name of the metal the way that it is, and then you take the name of the nonmetal, you drop the ending of the nonmetal, and you add IDE. Alright, so for example, we have barium chloride, which is Ba, barium, and Cl, which is chlorine. You drop the ending of chlorine and you add IDE. It's very simple. Let's try the next one. As you can see, it's a potassium and an oxygen, and what you would call it is potassium oxide. You don't have to denote the subscript of ionic compounds because, as I mentioned in class, ionic compounds only come together in one way. So you don't need to signify dipotassium or anything like that for ionic compounds. What about the next one? What do you think it's called? Well, the next one is a little trickier because you actually have to know that polyatomic ion, which is a hydroxide. So when you name ionic compounds that have polyatomic ions, you keep the name of the anion. So this would be magnesium hydroxide. I want to remind you guys that you need to be familiar with the common ions. I showed you the table during class, so please do not take that for granted. Please look at that and become familiar with the most common ones that I mentioned. What about the next one? The next one also contains a polyatomic anion, which is called nitrate. So you take the name of the metal and the name of the anion the way that it is. So it's potassium nitrate. Transition metal ionic compounds are a little bit different because, as I mentioned in class, they transition. They have different states that they can obtain. So you have to tell the reader what charge that transition metal has. So for example, if we have FeCl2, which is iron, and chlorine, you would have to tell the reader, if you're going to write it out in words, what charge does the iron have. You can use the uncrossing method, like I showed you in class, or you can set it up like a math problem. So we know that chlorine has a -1 charge, but we have two of them. So that would be 2 times -1 plus X, that's your iron, right, that you're trying to find out, equal to 0, because remember, ionic compounds only come together one way, so they have to equal 0. If you solve for X, you're going to see that the charge on iron turns out to be a +2. You can do the same for the next example, which is FeCl3. This is called iron 3 chloride. Set it up the same way with the math problem and you'll see you'll get a -3 for iron. I'm sorry, a +3 for iron. What about the last example? Cr is chromium and S is sulfur. The same applies as far as dropping the ending, but you have to denote the charge on the chromium. So we can uncross the subscripts like I taught you in class, or again set it up like a math problem. What you would do is you want to find the charge on the chromium, so you would put 2x, because you have 2 chromiums, plus 3 times -2, because -2 is the charge of each sulfur, equal to 0. So if you solve for that, you'll see that you'll get x equals 3 for the chromium. Other type of compounds we need to learn how to name are molecular compounds. These are nonmetals plus nonmetals, or if you have nonmetals plus a metalloid. They're very similar to what we learned with ionic compounds, except the only thing is that you have to denote how many of them are in the actual compound. But as you can see, the last element in the name also ends in IDE, so that's the same. I've included table 2.4, which shows you the common prefixes that we use for the different numbers, 1 through 10. You should become familiar with those. The first example I have is NF3. This is a nitrogen and a fluorine. Both of these are nonmetals, so we're going to denote it as nitrogen, which is the first metal, and then we have to say how many fluorines there are. There's 3 of them, so we put a tri in front of the fluorine, and we also take off the ending and add an IDE, so it becomes a nitrogen trifluoride. Notice that I do not say mononitrogen trifluoride. It is assumed if the first element is only 1, we just say the name without a prefix, so we wouldn't say mononitrogen trifluoride. Keep that in mind. Second example I have is sulfur and oxygen, but there's 2 oxygens, so how would that be called? I hope you said sulfur dioxide. The next one is nitrogen and chlorine, but there's two nitrogens now in the beginning, so this we have to denote. So that would be called dinitrogen tetrachloride. Try and do the last two by yourself. After some time, I hope you got it right. The second to last one is called nitrogen dioxide, and the last one is called dinitrogen monoxide. We do put the mono for the oxygen in the last example because, again, it's the last element, not the first element. To make sure we understand this concept, try to write chemical formulas for the following molecular compounds: sulfur tetrafluoride and dinitrogen pentoxide. The last part of Chapter 2 talks about naming acids and bases. We're going to learn a lot about acids and bases in later chapters, but for right now, we just want to teach you how to name them. I want to give you a definition. An acid is a substance that yields hydrogen ions when dissolved in water. There are some cases where two different names can be assigned to the same chemical formula. For example, if we were to see HCl, and with the stuff that we've learned so far, how would you call this? You would call it hydrogen chloride or hydrogen monochloride. But if we were to put this compound in water, it would dissociate, and that means come apart. So the H would be separated from the chlorine and attach itself to water. Don't worry so much about how this happens. We were going to learn that later. But for right now, realize that if you have a compound and it's dissolved in water and dissociates or gives away a proton, you have to denote that as an acid. This example I show you is, like I said, hydrogen chloride, but once it's dissolved in water, it loses a hydrogen proton and then it becomes hydrochloric acid. Other types of acids are called OxoAcids. An oxoacid is an acid that contains hydrogen, oxygen, and another element. The formulas are usually written with the hydrogen first, followed by that central element, which is some other element, and then the oxygen. These are some common acids that you will see often throughout this semester. The first one is called nitric acid. So as I said before, when you dissolve this in water, that H, that hydrogen that you see right there, will come off, will disassociate, and you'll end up with a proton, which is the H+, and then an anion, which is that NO3-. We have seen NO3- before. It's that one of those common anions that I told you needed to know. It's nitrate. The second example is carbonic acid. And when you disassociate those hydrogens, you get the carbonate ion, which we also have seen before. So what you need to realize is that anions that end in ATE, like nitrate, carbonate, phosphate, which also is one of those common ions that you need to know, when they become acids, they have an ending of IC, the ic. So nitric acid comes from nitrate. Carbonic acid comes from carbonate. Phosphoric acid comes from phosphate. There is a table in your book, table 2.5, which gives you a list of some simple acids that you should become familiar with. The last thing I want to talk about is how do we decide what endings it has besides just memorizing that if it comes from an ending of ATE, you need to put an IC as an acid. There is a figure in your book, figure 2.15. Let's look at that now. This table teaches us how to decide what to call oxoacids. So for example, if we start with a common one, nitric acid, HNO3, and I wanted to remove all of the hydrogens in this acid, I would move to the right, and that would tell me what anion it comes from, or what oxoanion it comes from. So nitric acid, if I remove all the protons, all the H's, they become nitrate. If, for example, I have nitric acid, and instead of removing an H, I remove an oxygen, so now it becomes HNO2, that would be nitrous, so I move down. And then nitrous acid, which would be HNO2, let's say now I want to remove all of the hydrogens, that becomes nitrite. So you see, this table helps us decide how we call these different oxoanions or oxoacids. Let's do another example, H3PO3, which is called phosphorus acid. Let's say I wanted to add one more oxygen, and instead of going down, I go up. So we started at phosphorus acid. If I add another oxygen, what would this be called? phosphoric acid, which is actually one of the common ones I told you needed to know. If I want to now remove all of the hydrogens from phosphoric acid, it now becomes phosphate anion. So practice these with different types of oxoacids and make sure you memorize the common ones: phosphoric, nitric, carbonic, and of course the corresponding anions that they come from.